This video will provide a brief introduction to the basic functionality of the Safe Zone Data Logging System, or SDL system for short, provided by Sensorlink and Cosasco. The SDL is the main control unit and data logger for the PipeMonit Swarm system. PipeMonit Swarm is a high-resolution erosion and corrosion monitoring tool based on ultrasound measurement technology. The Swarm system provides continuous and up-to-date monitoring of wall thickness changes in pipelines and vessels, in the short and/or long-term timeframes. Installation and operation is non-invasive, without any need to interfere with production. The SDL is certified according to ATEX and IEC-X for Europe and international, and CSA certified for Canada and US. The SDL data logger is installed in the safe zone, while the swarm sensors can be installed in the hazardous zone. The swarm sensors are connected to the SDL by a 2-pair cable. The SDL system is a data logger that is delivered with 4 parts: the SDL, the power supply, the intrinsically safe barrier, and the EX power supply. Other components necessary for the installation, such as terminals, cables, etc., are considered installation material and must be supplied separately on site. For further instructions on installation, see the user manual and terminal wiring diagram. The SDL is a small PC based on a Linux operating system. It performs 1 ultrasound measurement per sensor according to the fixed logging interval. The SDL records the measurement, calculates the wall thickness and corrosion rates, and makes the data available on Modbus or 4 to 20 mA interface. The data can also be retrieved using a USB memory stick, which will be shown later in the video. This is the main power supply. This converts incoming 230 volt AC to 24 volt DC for the SDL system. The SDL EX protection method is intrinsically safe. This means that certified IS barriers are required for the electrical signals, both for communication and power. This is the EX barrier for communication with the sensors. This is the EX barrier for powering of sensors. The SDL is powered by 24 volts DC. Plug in the power cord and the SDL will start booting. The boot time is approximately 30 seconds and the LEDs are not lit during boot up. If this is the first time you power up the SDL, it will be uninitialized. This means that the swarm sensors have not yet been recorded by the SDL. This is done by performing a baseline shown later on in this video. The uninitialized state is indicated by a slowly blinking pattern on LED 1, while LED 2 is unlit. To power off the SDL, you push button 1 and 2 simultaneously, and after 5 to 10 seconds, LED 1 remains continuously on and LED 2 is blinking rapidly. The SDL is now performing a safe shutdown. You can now either release the buttons or hold them in until all LEDs are unlit and the SDL is shut down. The SDL is now indicating an uninitialized state by blinking slowly on LED 1, whilst LED 2 is unlit. When in this state, the SDL will not be able to start any measurements before a baseline is performed. The baseline command records all the swarm sensors connected to the SDL. It is important that the sensors have been given unique addresses and correct settings prior to performing the baseline command. Otherwise, there will be conflicts between sensors having the same address. Unique addressing and optimum sensor settings are performed using the Sensorlink PipeView software and is not covered in this video. The baseline command is performed by pushing button 1 for approximately 15 seconds. First, LED 1 will remain on continuously, and then LED 2 will start blinking slowly and button 1 can now be released. The baseline has now started and will continue until it has scanned through all the sensors. The duration of this operation depends on the number of sensors attached to the SDL. After the baseline is finished, the SDL will go directly into active measurement mode. Active measurement mode is indicated by LED 1 blinking slowly and LED 2 blinking rapidly. One measurement cycle with 16 sensors will take approximately 2.5 minutes, but this will vary depending on sensor settings. When finished with the measurement cycle, the SDL will go into idle, which is indicated by slowly blinking on LED 1 and LED 2. The SDL will now perform measurement cycles at the configured logging interval, which is 30 minutes from the factory. Sometimes it is convenient to perform a forced measurement. This could be typically if the logging interval is once per day, but a measurement is required immediately. The forced measurement is performed by pushing button 2 for 10 to 15 seconds. LED 2 will light up continuously. Keep holding the button until LED 1 starts blinking slowly. You can now release the button and see that forced measurement mode is starting. Measurement data can be downloaded manually using a USB memory stick. This can be done in both the idle mode or the active measurement mode. Here, the SDL is in idle mode. Observe that LED 1 is blinking rapidly, which indicates that data is downloading from the SDL to the USB memory stick. The duration of this operation depends on the amount of data stored on the SDL. When download is finished, the SDL returns to its previous state, which in this case is idle. The data can now be reviewed on a PC. A complete download will create a new timestamp directory on the USB memory stick with the following content: a backup folder containing a copy of compressed raw data from previous downloads. The reference measurements folder is used for internal debugging. The Excel spreadsheet 2018 history contains all the connected swarm measurements like temperature, thickness, signal quality, and corrosion rate. A new history file is generated for each year. The Modbus map PDF file is the map generated during a baseline. All sensors connected to SDL will be listed in here together with housekeeping data of the SDL. COSASCO compressed archive files contain the raw data for each of the connected swarms. Each archive file contains one measurement cycle from all sensors. This is useful for post-processing and backup. The log file text document contains recordings from the SDL. Verification of correct configuration settings and software updates can be verified by looking at this log file. The regression window file shows the length of the current used dynamic window and is used for internal debugging. The system config file is the current SDL configuration settings. Lastly, the templates used for setting the SDL IP address and changing the configuration settings are found at the bottom of the folder. This will be described in a later chapter. Along with the downloaded data, a template for configuring SDL system settings via USB is included. We will now show how to change the logging interval and imperial or metric settings via a USB memory stick. Open the config file in a text editor. There are 5 settings that can be changed here: logging interval, imperial or metric units, speed of sound, temperature coefficient, and temperature offset. For users, it is the logging interval and imperial or metric settings that are most relevant, so we will focus on these two. From factory, the default logging interval is 30 minutes, and let's say we want to change this to 60 minutes. The data logger comes with metric settings set as default, and we want to change this to imperial. Save the file on the root of the USB stick and rename it by removing the word template. Close the folder and remove the USB stick. Wait until the SDL is in idle state and insert the USB memory stick. LED 1 will start blinking rapidly, indicating that an update is ongoing. Once finished, the SDL goes back into the idle state. The updates can be verified by looking at the log file that is now downloaded to the USB memory stick. Settings can also be verified by Modbus interface. If a static IP address must be set, use the template that comes along with the downloaded data on the USB. We will now show how to change the IP address via USB. Open the template in a text editor. Change the method from DHCP to manual. Information on IP, netmask, gateway, and DNS server need to be received from the network administrator. Save the file on the root of the USB memory stick and rename it by removing the word template. Close the folder and remove the USB memory stick. Wait until the SDL is in idle state and insert the USB memory stick. LED 1 will start blinking rapidly, indicating that an update is ongoing. Once finished, the SDL goes back into the idle state. The updates can be verified by looking at the log file that is now downloaded on the USB memory stick. The software of the SDL can easily be updated using a USB memory stick. Make sure that only the 2 files that are necessary for the software update is stored on the USB. Store the new software version on the root of the USB stick. To update the software version, the SDL needs to start with power off. When rebooting the SDL with a USB inserted, the SDL will scan for new software updates. We therefore perform the power off command, which is pressing in and holding down button 1 and 2 simultaneously. The SDL is now off, and we can insert the USB stick and the newest software version. To power up the SDL, we need to first unplug and then plug back in the power cord like this. The SDL will now power up and scan for software updates. After booting, the SDL will start the software update automatically, and this is indicated by LED 1 and LED 2 being continuously lit. This will take a couple of minutes. When finished, the SDL will go into uninitialized state and a new baseline needs to be performed. Remove the USB memory stick and verify software update by reading the log file downloaded to the USB memory stick.